Hello, everyone. I'm Haining, a postdoc fellow at MIT, and my advisor is Professor Beta Gallant. We are working on a new type of primary battery, or non-rechargeable battery, that can deliver the highest energy density on the market. So primary batteries has a market size more than 30 billion, although they are not rechargeable, but they can last for a really long time. In fact, some of them last for so long that you probably won't even notice that there's a battery inside. For example, the pressure monitor inside the car tire, or the Easy Pass, the one for toll collection. And the reason why those batteries can work so well is because they can have energy density more than 3 times higher than the rechargeable system. And this makes them irreplaceable, especially for those applications where recharging is not possible or impractical. For example, for a medical implant like pacemaker, or unmanned vehicles for defense applications, and sensors for remote monitoring and Internet of Things. Take pacemaker, for example, which is a basic life support device. A typical pacemaker battery can only last around 5 to 10 years. And after the battery died, we need surgeries to replace the battery. Then you may be wondering, why can't we just make longer lasting battery for this? All we need is just a higher energy density. Well, unfortunately, primary battery market has been deemed quite mature, and there hasn't been any major innovation in the fundamental cell chemistries in the past 40 years. And thanks to the advancement in organic synthesis, we developed a new type of primary battery based on liquid fluorinated reactant, or we call it LFR. So LFR has 2 major characteristics. First, it is fluorinated. That means it intrinsically has a very high energy density. And second, it is also liquid. And why does this matter? Well, this means it can function both as a cathode active material and the electrolyte. That's why we call it a catholyte. Let's take a look inside a battery. A traditional battery on the left, here we take CFX battery, for example, which is the current energy leader. CFX is a solid, so it's a black bar in the middle, and we need to fill this battery with liquid electrolyte. But electrolytes are electrochemically inactive, so they cannot store energy, they're just dead weight. With LFR, we can replace this dead weight with our LFR catholyte and turn it into an active phase. So the battery materials are more efficiently used for storing energy. And this contributes to an even higher cell level energy density. And here are the performance achieved so far. With our lab scale setup, we already showed that we can successfully boost the energy density of the current energy leader, the CFX battery, by 20%. And our calculation shows that with better cell structure optimization, an even higher number, a more than 50% improvement over CFX, is achievable. And this high energy density will translate to important value propositions, such as extending device life, or decreasing device size and weight, and also to reduce maintenance cost. For pacemaker or medical implant, this means fewer invasive surgeries for patients. For example, a 50% improvement, meaning that the pacemaker can last 5 years longer before a battery replacement is needed. Or for defense applications, this means a longer critical mission operation. For drones, for example, this means they can fly to 500 miles away with one single battery. We've developed 3 generations of our LFR so far and filed 3 utility patent applications along with that. And our work has been published in many journal articles. And after we optimize the cell structure, we can then take advantage of the current manufacturing system and become a drop-in technology to the current manufacturing line, with the only key modification being the electrolyte filling step. And the projected cell level cost will also be lower than the state-of-the-art, because our battery uses less amount of inactive component, which is this yellow area. So this is saying our battery can enable a longer battery life, a smaller size and weight, at the same or even lower cost. We've talked to more than 30 potential customers and received many positive feedback, and we identified the medical and defense markets being the most promising options for our initial market entry. And here's our plan for the technology development. So our key next steps is to scale up our battery, both in size and in capacity, and also to demonstrate battery reliability. And we're planning to spin out in the very near future. So currently, our team only has me and my PhD advisor, Professor Beta Gallant, But we are very lucky to have support from many MIT entrepreneur programs, and especially would like to thank the support from Dashboundary Center. And we'll be at the poster session, so come talk to us. We will appreciate any input on the business model or the manufacturing options, and we will also appreciate any connection to potential investors and team members. And thank you, everyone. Looking forward to talking to you.